Morein researchers at the Indian Institute of Technology IIT Ropar, Punjab, and IIT Mandi, Himachal Pradesh, have utilized the overexpression of biotin receptors on cancer cells and enhanced production of thioredoxin reductase (TRXR) enzyme in cancer cells for cancer diagnosis. Breast and cervical cancer cell line studies showed encouraging results. The researchers developed a hybrid of assembly by binding naphthalimide moiety to carbon dots using disulfide covalent bond. Naphthalimide analogs are used as anti-cancer agents. In the presence of normal amount of TRXR enzyme seen inside normal cells, the carbon dots behave as an energy donor and the naphthalimide moiety as an acceptor, thus establishing fluorescence resonance energy transfer FRET. There is a typical yellow emission when irradiated with visible light. But in the presence of elevated levels of TRXR enzyme, which is seen in cancer cells, the disulfide covalent bond gets disrupted, freeing the naphthalimide moiety from the surface of carbon dots. As a result, the FRET gets disrupted and there is blue emission when the cells are irradiated with visible light. In normal cells, the amount of TRXR enzyme is very little and hence the FRET mechanism is not eliminated, resulting in yellow emission. Color reveals we can distinguish cancer cells from normal cells by the color of the emission. The presence of yellow emission indicates normal cells while blue indicates cancer cells, says Dr. Narinder Singh from the Department of Chemistry at IIT Ropar and the corresponding author of the paper published in the journal Axe Applied Materials Interfaces. Unlike normal cells, cancer cells have a large number of biotin receptors. Since biotin is present on the surface of carbon dots, the hybrid of assembly is absorbed in large numbers by cancer cells. Within 3,045 minutes of treatment, we could see the change in emission from yellow to blue. The blue emission could be seen up to 2 hours after its appearance, says Dr. Singh. When the bond is intact, the emission comes from the naphthalimide moiety, and when the bond is broken, the emission comes from the carbon dots, says Jagpreet Singh Sidhu from the Department of Chemistry at IIT Ropar and the first author of the paper. The band gap between carbon dots and naphthalimide moiety is different, leading to different emissions. Since visible light cannot penetrate human tissue, the potential application of this technique may be during surgery to no tumor spread. We will know more about its applicability only during animal studies, he says. Therapeutic. The naphthalimide used here can also function as a cancer therapeutic. The nanosensor was found to reduce the viability of cancer cells up to 70%. The naphthalimide that gets released when the disulfide bond is broken is responsible for the destruction of cancer cells. We had used higher concentration 100 microgram per milliliter of naphthalimide to kill 70% of cancer cells. Usually, much lower concentration of drug is used for therapeutic purposes, says Ashutosh Singh from the School of Basic Sciences at IIT Mandi and one of the authors of the paper. Since naphthalimide is expensive, the researchers are trying to develop a cheaper substitute. We will test the new hybrid material on more cancer cell lines before testing it on animal models. The focus is on using the assembly for diagnostics. If it offers therapeutic benefits, then it will be an added advantage, says Dr. Singh.